Mastering data structures through hands-on projects in today's fast-paced tech industry, demonstrating practical skills is essential for standing out in competitive job markets. For aspiring software engineers, data structures form the foundation of efficient coding practices. Data structure projects provide an excellent way to apply theoretical knowledge while building tangible solutions that showcase problem-solving abilities. These hands-on experiences help bridge the gap between classroom learning and real-world applications. The power of practical learning hands-on projects allow learners to explore complex topics through experimentation rather than passive consumption. This active engagement fosters deeper understanding and retention of key concepts. Demonstrating proficiency in implementing data structures gives developers a significant advantage when applying for technical roles. Employers value candidates who can translate theory into working code. Creating functional implementations helps solidify abstract concepts like time complexity and space efficiency. The process of debugging and optimizing code reinforces fundamental principles. Essential project categories. There are several project categories that effectively demonstrate mastery over different aspects of computer science. Choosing projects aligned with personal interests ensures sustained motivation during development. Algorithm implementation projects teach how to translate mathematical concepts into working programs. These projects often involve solving classic problems using various approaches. Graph algorithms implement BFS/DFS traversal, shortest path finding, and minimum spanning tree generation. Sorting algorithms code quicksort, merge sort, heap sort, and their variations. Search algorithms develop binary search trees, tree structures, and hash table lookups. Data structure visualization tools offer great educational value by making abstract concepts concrete. Creating interactive visualizations enhances comprehension for both developers and end users. These tools transform static diagrams into dynamic representations that show how operations affect underlying data organization. Interactive elements make learning more engaging and intuitive. Developing such tools requires combining algorithmic knowledge with front-end technologies. This combination creates versatile skill sets applicable across various domains. Optimization challenges. Efficient memory usage remains one of the most critical challenges in modern computing. Developing optimized data structures directly addresses this fundamental concern. Caching strategies represent another crucial area where effective data structure implementation makes a noticeable difference. Proper cache management significantly improves application performance. Cache-friendly data layouts minimize CPU stalls by keeping frequently accessed information readily available. Techniques like spatial locality optimization become essential at scale. Benchmarking implementations against standard libraries provides measurable validation of design choices. Comparing performance metrics helps identify areas for improvement. Real-world applications. Many successful companies have built their core systems around innovative use of data structures. Studying these examples reveals patterns common among high-performing applications. Google's PageRank algorithm revolutionized web searching by leveraging graph theory fundamentals. The distributed architecture handles massive datasets efficiently through clever structural choices. Amazon's recommendation engine demonstrates advanced application of associative arrays and matrix multiplication techniques. Personalization features rely heavily on optimized lookup mechanisms. Facebook's newsfeed algorithm combines multiple data processing layers. It uses priority queues for sorting content based on relevance scores calculated from user interactions. Building your own projects. Selecting appropriate projects depends on individual goals and current skill levels. Beginners might start with simple implementations before moving to more complex systems. A good starting point could be creating a custom linked list implementation with basic operations. This builds foundational understanding before tackling more sophisticated constructs. Moving beyond basics involves experimenting with self-balancing trees like AVL or red-black implementations. These require careful handling of rotation logic and height calculations. Advanced learners might consider developing a full-fledged database system. Building query processors and indexing schemes offers deep insight into persistent storage mechanisms. Game development presents interesting opportunities for applying graph theory concepts. Pathfinding algorithms used in AI behavior benefit greatly from efficient data representation. Collaboration opportunities working on open-source projects provides exposure to professional-grade codebases. Collaborative environments teach best practices through direct interaction with experienced contributors. GitHub hosts numerous repositories focused on algorithm implementations. Contributing fixes or adding new features builds portfolio content while gaining peer recognition. Participating in hackathons introduces pressure testing scenarios. Time constraints force creative problem-solving under deadlines similar to real-world conditions. Joining online communities allows sharing progress and receiving feedback. Engaging discussions help clarify doubts and discover alternative approaches. Coding bootcamps often feature collaborative group projects. Working with others develops communication skills alongside technical expertise. Evaluating success criteria measuring project success goes beyond mere functionality requirements. Performance benchmarks serve as objective indicators of quality implementations. Time complexity analysis confirms whether chosen data structures meet expected efficiency standards. Space complexity considerations ensure sustainable growth potential. User interface usability becomes crucial when creating educational tools. Clear visual cues enhance understanding without overwhelming viewers with too much information. Code maintainability factors influence long-term viability of any solution. Clean architectures with well-documented components facilitate future modifications. Future trends and innovations, emerging technologies continue shaping what constitutes relevant project experience. Keeping pace with these developments expands career possibilities. Quantum computing research demands new approaches to classical algorithm design. Early adopters gain advantages by exploring novel computation paradigms. Artificial intelligence integration opens exciting avenues for innovation. Combining machine learning models with traditional data structures produces powerful hybrid systems. Distributed systems engineering benefits immensely from concurrent data structure implementations. Handling parallel access requires careful synchronization strategies. Blockchain technology relies heavily on cryptographic data structures. Exploring Merkle trees and Patricia trees provides insight into secure data verification methods. Conclusion: hands-on projects remain the most effective way to master data structures and algorithms. They enable practical exploration of theoretical foundations through direct implementation. Continuously refining your portfolio with new projects keeps skills sharp and marketable. Each completed challenge adds depth to your technical narrative while preparing you for evolving industry needs.